So, welcome back to my channel, friends. So today I'm not continuing my classes for 12 now. So today I will talk about an important topic in mathematical physics, which is the Green's function. So Green's function is basically used to solve differential equations. So differential equations. Some examples of differential equations in physics are the Laplace equation, which is given by del square phi equals 0. This is an example of homogeneous differential equation. So I am writing differential equation as d dot e for short. Also, example of inhomogeneous differential equation is the Poisson's equation, which is given by del square phi equals minus sigma by epsilon naught, which is an example of inhomogeneous differential equation. So using the Green functions, we are going to solve this type of problems, these types of equations with certain boundary conditions which are available to us. So I have to mention one point is that if I have a homogeneous equation, I am writing homogeneous equation as in short as HE is subjected to some inhomogeneous boundary conditions. Then it is equivalent to inhomogeneous. I am writing for inhomogeneous as IHE. Inhomogeneous equation with homogeneous boundary conditions. So what I mean is that if I have an equation, then the equation is homogeneous. That is the Laplace equation. Let's do the Laplace equation. So what I will have is that if I apply the some inhomogeneous boundary conditions to this equation, to the homogeneous equation, then this equation can be think as a inhomogeneous differential equations with homogeneous boundary conditions. So I am going to prove this also. Then I will follow up with the Green's function. So what I have, let us consider a homogeneous differential equation as this. So where L is some differential operator, L values varies like d by d, like this. So what I will have, if I impose this homogeneous equation with some inhomogeneous boundary conditions, like I have some psi equal alpha at a point x equal a and some psi equal beta at some point x equal b, this type of inhomogeneous boundary conditions. This is the inhomogeneous boundary condition and this is the homogeneous equation, homogeneous differential equation. So if I impose this boundary condition to this equation, what will happen? It will behave like a inhomogeneous equation with homogeneous boundary condition. So I am going to prove this. So for this, let us see a function ux equal psi x minus vx. So this function vx has the same characteristics as this function. So at some point a, this function will also have the value alpha, and also at some point b, this function also have the value beta. So if I use this equation 2 in equation 1, so what I will have? I will have L, I will substitute for psi here ux plus Vx equals 0. Okay, so Lux equal minus of Lvx. So Lux equal minus of, not minus of, Fx. So where Fx is equal to minus of Lvx. So what I have, you are getting this point? I have started with the homogeneous equation, but I have left with some inhomogeneous equation. I have something on the right side which is a function of x also. So this is a inhomogeneous equation. This is a inhomogeneous equation. And what are the boundary conditions of this equation? Can you guess? So the boundary conditions will be like, let us say, if at a point A, psi x has the value alpha and Vx also has the value alpha. So what will be the value of Ux? Ux will be, U at a point alpha will be 0 and U at a point beta will be 0. So these are the boundary conditions imposed with this equation. So what I get? I get a inhomogeneous differential equation from a homogeneous differential equation with homogeneous boundary conditions. So this type of questions with inhomogeneous boundary condition, or itself the differential equation, if it is inhomogeneous, then I can go with Green's function to solve this question. So moving on, see what I got is Lux equal Fx. So here the term Fx is known as source term. Remember that this term is known as source term. With this term I have to solve the equation, but I am going to introduce a Green's function with a unit source. Remember that I am going to introduce the Green's function with a unit source, not the source term. If a source term contains like 1000 of something, then I will only consider one of it to introduce the Green's function. Clear? So I'm going to introduce the Green's function like introducing the Green's function with unit source. So g of x dash equal minus So I am going to introduce the Green's function as some solution of the homogeneous differential equation I have considered. Not that I have considered it earlier that let L psi equal 0, but what I am getting is I am just replacing this psi from G. So I am treating G as a solution of psi, but for only the inhomogeneous equation, because I have some source term in the right hand side in the inhomogeneous equation. But what I am taking right now is I am taking a unit response. I am taking some unit response by using the canonical delta function. So this is the Green's function. This is the Green's function. This is the Green's function I have. So I have introduced the Green function here, and this Green's function have also some boundary conditions at some point x equal a and x equal b. So with this I am going to get my whole solution as the whole solution for a term fx, because this is a source term. This will be calculated as minus infinity to plus infinity. I am going to integrate with the Green's function. I am going to integrate with the help of Green's function my solution. Let us consider this interval as some a and b, because I have some boundary condition imposed on the Green's function also. So I am going to integrate it from minus a to b, because I have the solution for fx at only these points. At other points the value of g will vanish. Okay. So this will be the solution. So I am directly going to the analysis of the Sturm-Liouville equation for getting the behavior of G for one-dimensional case. So the Sturm-Liouville equation is some kind of equation which can be related to other physics and engineering problems. So I am going to start with this. So the Sturm-Liouville equation, the operator L for the Sturm-Liouville equation can be written as ddx of px ddx minus qx. Okay. So for some function psi, it will be replaced by psi and psi x you can consider. So this is the equation, differential operator for the Sturm-Liouville equation. So I am not going to do the whole analysis here. I am not going to derive the equations here because I don't need it. For examination like entrances and also for questions. So I am directly going to introduce the solutions of the Green's function. So I will mention the steps how I have to calculate the solutions. So what I will get is g of gx dash equal. So this is the Green's function I have evaluated for the Sturm-Liouville equation. I have not shown the calculations here. So this is minus of ux into v of x dash divided by a, which is for the interval a to x dash, and u x dash into v of x divided by a, which is for the interval x dash x to b. So what I have, this ux and vx are the solutions of the Sturm-Liouville equation I have considered. So what I have got is that I have got that the derivative of the function g at some point x plus epsilon dash is minus dg by dx x minus epsilon dash is not continuous. It has some discontinuity at some point x equal x dash. So I have to divide it in two parts, g1 and g2. So I am getting two solutions of the Green's function as this and this. So I have to remember two properties of the Green's function always. The first one, that the Green's function is always continuous in the interval a to b. This is the open interval a b. And the derivative of the Green's function has a discontinuity at some point x equal x dash. So here the a is a constant which can be evaluated as px dot w. W is the Wronskian here. So we all know about the Wronskian. Wronskian is given as u into v and u dash into here v dash. So if I have a question given, so what I will do, I will consider some solutions of it like u and v. I am going to evaluate the derivatives. Then I will work out for the Wronskian. Then I will evaluate the a. Then I will evaluate the Green's function. Then I am going to get my solution. So for example, I am going to take an example. So this is one type of example I am taking. So I will consider u and v. So let me give also the boundary conditions. So the boundary conditions are like this. These are some solutions at x equals 0 and at x equal 1 equal to 0. So what I will do, I will consider two solutions of the equation. I will consider u and v as the solutions of this equation first. So what I can do is d square u dx square equals 0 and d square v by divided by dx square equal 0. So I will have to evaluate the u for this. So what I will do, I will integrate it simply. What I will get some du by dx equal a. Again I will integrate it. I will get u equal x plus c, but I have some boundary conditions at psi equal u, psi equal 0. So what I will get is that the boundary conditions that psi is going to follow is also followed by its solutions. So the function u, I have considered here is for the interval a x to x dash, and v is for x dash to b. Okay, so u is going to follow these boundary conditions, and v is going to follow these boundary conditions, because these are the values of a and b. These are the values of a and b. So if I considered the first boundary conditions u is going to follow, that is u is 0 at 0, then I have this will 0 plus c, so c equal to 0, then my solution will evaluate it as u equal to x. Okay, then for this equation what I will have is v equal similar solutions I will get. So let it written as this. So imposing also the boundary conditions, v equal 1 at 0, so c into 1 plus b is equal to b equal minus c. So what I will get, v equal minus c, so I will put here minus b, minus b x plus b 1 minus x. So this is my solutions. This is the solution 2 and this is the solution 1. So I have to work out these solutions. So let me write the solutions. So I have u equal ax for the interval a x dash to x, and v equal b 1 minus x for the interval x dash to x to b. Okay, so I evaluated the solutions of the equations. So let me evaluate the Wronskian first. So Wronskian's, like, it will be 1 minus x. This will be a for u dash, here u dash, which is going to be a, and for this what I will have, b minus bx, so this will be 0 minus b only. Okay, so a into x, ab x minus of b, ab minus, this is minus, this is plus abx, so this will cancel out, only ab will remain. So this is my Wronskian. So with this I have to evaluate my a value. So let me consider this at a dash, okay, because I have some constant a also. So this will be considered as a dash, this constant. So what is a? A is px dot w. So what is px for this equation? If I consider this equation with my Liouville term, what I will get is this px d square x minus of qx. So here for this equation q is 0, you can simply compare with it, and for px it will be 1 to get d square by dx square simply. So px will be 1 for this equation. So px will be 1 and this is ab. So I am getting my as minus ab minus a dash b. Okay, I am considering this as a dash. So after this I have to calculate the Green's function. I have to calculate the Green's function as, simply I am going to calculate the Green's function as, what are the values of the Green's function? As you have written, this is ux, vx, this is minus a divided by a for the interval x dash, and for the interval x dash to x b. So I will follow up with the so what is the value of ux? It is a dash x. And what is b dot x? This is b1 minus x dash, because it is a function of x dash, and divided by a dash b, which is a minus of a dash b. So this is for the same interval here. So for us dash is a dash x dash, and for b is this 1 minus x divided by a dash b. This is also minus, this is also minus, so this minus will be cancelled, a dash cancelled, b cancelled. So my solution will look like this. These are my solution for the interval mentioned here. So with the solution, I am going to calculate the solutions of the given differential equation by simply integrating this function with fx for the interval minus a, not minus a to b. For the interval a to b, I will integrate the function g with fx. Then I will get my whole solution. So I will follow up for tomorrow. So with this, I conclude my lecture for today. Good night.